Okay, good evening all. So today class day 4, right? Class day 4 today. So far we have discussed 3 classes. So today, Hare Krishna, are you there? Hare Krishnan.
Hello, yeah. Raghavji, can you hear me?
Yeah, I can hear you, Hari. Yeah, yes, I can hear you. So Hari, just before the class, we are discussing with Hari. Hari is working as a substation O&M engineer, operation maintenance engineer, and now they following my classes videos and the live classes they are following, and they got selected in a company for a design engineer of the substation. So like they changed the profile from O&M into the designing, which was their target to join the classes. Right, Hari? Am I correct?
Yeah, you're right.
Yes. So I told Hari to share your feedback, your interview questions, what like questions you have been asked during the interview, and about your personal feedback to other participants, so that others, when they are starting this training program, they can prepare themselves accordingly. Right, Hari? So
Yeah.
just briefly, not in the detail, but briefly in 4 or 5 minutes, share your interview process with others. And like similarly, there are many testing, commissioning engineers, O&M engineers who are looking to change their career into the designing field. So that will helpful for them as well. Yeah, okay. Over to you, Hari. Now you can speak.
Yeah, thanks, Raghavji. Hi guys. Happy to talk to you about this. I was in contact with Raghavji for past 1 year. I couldn't join his first batch. So this one I managed to join, and in that case, I wanted, start as early as possible, but as we regard some problems, it started a bit late. So he offered to actually give me some recorded versions of his previous classes, some, important modules. So I started my preparation from that. Uh, so actually, I attended three, four interviews until now, and last 3 months were actually, failures, and part of which was the role I was applying for. I tried protection as an engineer, but that sort of sophistication we can't get from, anyways, we can't get it from classes. So then I tried on design. I almost made it to second round, but again they were looking for a gas insulated switchgear design background, so I couldn't yet again break through. But this one actually, I prepared some more, took a lot of time into this his classes, and it really helped a lot. I think, as he said in his previous recorded classes itself, we had to, 90% is on ourselves. We had to learn ourselves. That's the first thing. And yeah, I think the most important thing is to pay attention when he's speaking. Don't interrupt him. That's the main thing, in my opinion, because he will touch every point. If we have any doubt, also we should, try to keep it ourselves and then clarify it later, because he will anyway. In my opinion, I have seen it in recorded classes that he will touch those points anyway. So the most another thing we should all we concentrate on is whatever domain we are looking for, we are working. If it's substation, we should be familiar with everything that's related, even if it's a small thing. Because in my last interview, actually they asked me about PLCC, power line carrier communication, which was in actually some our specialization. Like, it's not important in perspective of electrical engineer as per se, but still Raghavji gave us a small idea about that. So they asked me about PLCC, why wave trap is connected. after CVT? Why? No, that sort of logical questions they always ask. So we should be very well familiar with the SLD's selection of switch gear, everything like that. So actually we should pay attention to the classes and concentrate on what's the role we are looking for. If it's a design, we should be very good with IEC standards. We should probably by heart some because they ask you like out of the blue they ask you what's the IEC standard for instrument transformer, what was the old standard, what's the difference in new ones and this one. So we have to get a small idea about what's the new market, why SF6 is what's the new change in happening in SF6 switch gear, why it's being discarded. Yeah, like that sort of we should actively in my it's a personal opinion, we should actually also have a good LinkedIn profile, because having a LinkedIn profile will greatly help. Because in my last interview they asked me, what do you know about the company, why do you want to join the company? And so I did a small background research on the company, so I knew about their latest acquisitions, etc. So when they said when I said it when I mentioned it, they were really pleased about it. So actually having a LinkedIn profile will greatly help you having connections and also learning about new whatever is happening in the market, power market right now. So basically, yeah, I think if we pay attention to the his whatever his opinions, his suggestions, and also if we if we have a clarity about what we are what's the role we are looking for. If it's protection, we have to not only from his input, but we have to create our own inputs also. From
Yeah.
protection is a vast field, similarly design. So yeah, that's pretty what
Yeah.
I have to say. Yeah.
Thanks, Hari. So I think Hari, is it okay that you can tell your company name one participant asking that you feel comfortable?
Sorry, Raghuji, I couldn't. Yeah, you asked.
Avijit asking which company you have joined. So
Yeah,
understand.
I joined HNMB, high
So
voltage and medium.
yeah, so HNMB is an Ireland and UK based company. They have office in India as well. In Bangalore, they have office,
Yeah,
right?
Bangalore. Yeah, Bangalore. Yeah,
In Bangalore, they have Indian office, but they do project in UK and Ireland. For the
yeah,
HMB, the main client is the ESB. ESB is the Electricity Board company, which is based in the Ireland. And ESB is the utility company of Ireland, and they work parallelly in UK as well. So SS HNMB work for the SSC and few national grid project as well in UK. So when Hari will join the company and when he will work, so he will work for the Ireland and UK country-based project as a design engineer for the service stations. Currently, he is operating the service stations as an O&M engineer. Okay.
yes,
Great,
yeah.
congratulations, Hari.
Yeah, yeah, Arvind. So, okay, so let us move on. Let us move on to the classes.
Oh, thank you.
Thanks for sharing your experience, your feedback. Okay. So the main point is that what we are discussing in the class, please do not interrupt. Listen the classes very sincerely and follow each and every sentence. We are covering the entire service stations, entire interview questions. And when interview is not more important, important that when you selected whether you are capable to do the project or not. So in that way, we are covering that you can work independently as a design engineer, which is most important thing. By the chance you clear the interview, but if you could not perform during your probation period, then your job would not be permanent. So, which is more important than cracking any interview. Okay, yeah, thanks, Hari, again, and congratulations to you. And this is good thing that you share your feedback in the beginning of this training program so that others can take the benefit. Okay, so let us move on to the class day 4. And before the class day 4, let us summarize what we have discussed in class day 1 and class day 2. Yeah. So in class day 1, we discussed the major component of electrical power system network And in class day 2, we have taken the ETAP software. Their introduction we discuss, and then we discuss the comparison between the, like we discuss what is the power evacuation or transmission voltage uh, preferred or selected for the grid connected solar power plant. And once the solar power plant is connected to a grid substation, so what is the medium of power transmission, whether we should go with overhead line or we should go with the underground power cables. So that comparisons on class day 2 we discuss. And on the class day 3, we started the detailed designing. And for the detailed designing, we discussed that what is the substation project main sources, main company source who like produce the job of the substation in the market. So these are the some example of the main source. And then we discuss what is the main utility company. So we took example from the different country and their utility name. Like in Nepal, we have an EA, Nepal Electricity Authority. I have one engineer from the Nepal Electricity Authority, Umesh, who joined our training program. So he working as in Nepal Electricity Authority as a government engineer. And then SEC, SEB, PGCB, we have engineer from the PGCB as well. Then National Grid and SSC. My last batch student, he selected in National Grid and SSC, both the company. One Grid, Ireland, ESP, like that. These are the main utility company for the different countries. And then we discuss about then we took one project, and for that we downloaded one live project from the which portal we have used for that. We downloaded one live real project from REC, right now, Rural Electrification Company. So we downloaded one real live tender from a company, REC company, and then we discuss how to start the designing work for the project. So in that we discuss the first thing that we will check what is the your company scope of the work and have a correct understanding about the scope of the work. This is we discussed first step, and then we discuss that in the scope of the work, all scope given in the sentence called bay, like line bay, transformer bay. Let us open this again. I think this is the tender that we have downloaded, right? In the last class, correct now? This is a project that we have downloaded.
Yes, sir. Yes.
So in this project, we discuss the first, we will check the scope of the work. Just one second. The scope of the work. One second. Let me open it again. One second, yeah. So here we have the scope of the work that we have discussed. So in this scope of the work, the most of the sentence written as line bay, bus coupler bay, tertiary buses, transformer bay. So we discuss in class day 3, what is the meaning of the bay? What is the meaning of the bay? So we discussed that before coming to the way, we discussed that in the substations we have a common bus bar. So for that we took this example. Just one second. Yeah, we took this example, and we have discussed that in the substations we have a common bus bars, common bus bar. This bus bar could be the flexible conductor, or it could be the rigid tubular bus bar. For that, we use the IPS tube to make this bus bar. That we will cover in module number 4, the comparison between flexible conductor bus bar and the tubular bus bar, and for which side, what kind of the bus bar we should take, whether we should go with flexible or we should go with the tubular bus bar. That comparison we will do. So we discussed that the substation is made by a common bus bar, and this common bus bar is divided into bays. That all we discuss. Have a common bus bar, and these bus bar are distributed into bays, such as this bay could be line bay, transformer bay, and if my voltage rating is 400 kV and above, in that case, if we have a long transmission line, in that case we use the reactive power compensation device. This is called shunt reactor, and the bay or circuit which is connecting reactor to the bus bar, that bay we call it the reactor bay. So this we discuss, and then we discuss bay means bay represents a circuit connection in a substations. If I'm connecting a line circuit to substation, then that circuit I will call as the line bay. If in case I'm connecting a transformer circuit to a bus bar, then that transformer circuit connection to bus bar we will call as transformer bay. So that all we discussed, uh, right? And then we have this seen some few site photos to understand about the bay. So like this photo we have taken, and we understood here in this particular site we have two transformer bay. This is one transformer bay. This is second transformer bay, and we have this common bus bar. And here we have the one transmission line bay. This is the bus PT that we have used here to check the voltage of this bus. This all we will discuss in the SLT model about the bus PT, right? So we took this example, and here we have some, this is in this particular site photo, we have the tubular bus bar, and this two circuit, which is one here, second here, this will form the connection, or it will be a line bus bar. This is called as the tower, and this is called as the beam, and the whole thing called as the gantry or line gantry. So this line gantry will provide the connection from the transmission line, and then we will take drop on the equipment, and through the equipment we will connect to the to this common bus bar. And from this common bus bar, again we will take the drop and connect to the transformer. And this, like in this particular case, we have like 5 transformer bay, and we will have 2 line bay, right? So we took this example as well just to understand about the bay. So after understanding the bay, we discuss about this complete scope of the work, and after that we discuss that the second step would be, we will collect or arrange or ask to my project manager, project management department, or client, that what is the list of deliverables, or what is the list of the drawings and calculations that we have to create for the substation project. Based on that drawings, the site construction will be performed. So we took that, we will take in the project if it is given, if it is not given, so we will ask. And generally we took the example that we have taken one reference from the Power Grid India, that in the PGCIL India, when they issue a substation tender, so what is the list of the drawings and document they ask to submit from their EPC contractor. So that list we are referring here in this training program. And this is the 99%, this list is common to any kind of the substations. 1 or 2 document additionally any company may ask. So for you take this reference, this separately we have discussed this document, that this is the drawings and document you have to prepare. So you have to develop your skills so that you can prepare these drawings and calculations, right? This all we have discussed on the class day 1. So please refer the class day 1 discussion. Now, step number 3, we discussed that after checking the scope of the work, after checking the list of the drawings and calculations, what we will do, like how we will proceed with the project. So for the project, we will study the project technical specifications. So this is the project specifications. This is 1800 page specifications approximately. So no need to study all 1800 page of this technical specifications, because this is a common specifications for all, for the electrical, civil, commercial, each and everything covering in this specifications. So what I will do, I will check my major point. So what would be the major point that we will discuss today? Right. So we will study the technical specifications, and sometimes during the project award or tendering time, if any scope is not clear, so EPC company reach their clarifications. So the client will response on their clarifications. So we have to also check if any bit clarification. So that bit clarification is also important to the design engineer. Do not miss this clarifications document. Do not understand that this is bit clarifications. So this is not linked with the designing. This will link with the designing as well. So need to study the bit clarifications document as well, whether like all the steps at least you go through. If anything related to the design, that point you note down. If not, so you can just once go through. No need to thoroughly go through, but just don't go once go through. So this two document we will study, and we have discussed that before working as a design engineer, we should have the knowledge, prerequisite knowledge. The prerequisite knowledge is the for the electrical system, for the high voltage electrical system, what is that particular country grid specifications or country specifications. So that knowledge we should memorize. So like local country electrical grid requirement, this we should memorize. So I have requested all of you that please memorize this specifications. And particularly if we talk in India, so we take the CEA, which is the company which publish the grid specifications. So we need to memorize this during this training program. So that will directly help during your designing when you are working as a design engineer. And if you have started as a design engineer, you could not memorize these things. So keep this document with you, and whenever you get the time, you at least study 1 page or 2 pages on your daily basis, so that you will be updated with the requirement. And four things that we should aware, and this is also interview questions, that we should also aware the standard, applicable standard for the designing, like what is the IEC standard, what is the IEEE standard, and what is the name of the standard that we should follow. At least when we should the name, we should memorize the name. We can tell during the interview time. Further, during the designing also, we can refer that standard. So that is standard. So during this training program, we will take all the standard which is utilized. And again, in the standard, we have 300 page, 200 page like that. So all 200 page, 300 page, no need to study in the beginning. We will take up what is the relevant page, so that at least you memorize the relevant page and the relevant clause of that standard, which will directly help you during your detailed designing. And we discussed that even though we are following 4 different guidelines, so on a particular topic, on a particular sentence, if there is a conflict between all 4, so which will supersede. So that we discussed that the more stringent will supersede, and by taking the consent of the client as well. Right. So this all we have discussed during the class day 3. So here we listed all the standards. So please note down all the standards in your pen paper and try to memorize these standards. And Hari Krishnan also telling this point for your interview. So I took the example of the some standard regulations, that when we are going through the standard regulations, so we should know their requirement. So here we took the example of the surge arrestor, that in the surge arrestor, it is the grid requirement that we should follow. So this is all the example that we took to explain you the importance why we should aware with the grid specifications and the requirement. And here I took the example of the clarification, that here through this bit clarifications we came about this particular losses of the transformer. So when we are purchasing the transformer, we will make sure that losses given by the transformer manufacturer should be as per the client requirement. Right. So this all is the class day 3 discussion. Am I clear so far? Day 1, day 2, and day 3. Could we now go to the class day 4? Any?
Yes, please, sir.
Yeah. So before proceeding with the next steps, I have discussed so far the 3 steps. Before proceeding to the next step, uh, I'm taking a little bit more time, and I wanted to tell you one important concept. So the concept is that if I take this specifications, could you see here in this particular work scope, the sentence is 220 kV transformer bay. At the same time, if I'm opening another scope of work, this is the same company REC, the same company REC. Here again the same company REC, which project we have downloaded, REC Power Development and Consultancy Limited. So the same company, I took the another project, which is another voltage level. So this is the 220 by 33 kV. 220 by 33 kV. You can see the voltage level of the substation. In this case, the voltage level is different, and the voltage level is 400 by 220 kV. So could you see the difference here? They are using the ICT word, and in this particular, they are using the transformer word. So what the difference between both the transformer and the ICT? So line bay is similar, line bay here, line bay here. So it is both is the similar same word, same sentence. But here for the they are using ICT bay, here they are using the transformer bay. So let us understand about this difference as well. So generally, I'm telling generally means I do not have any IEC and IEEE that I can tell you that I'm taking this my statement from this IEC. I'm taking as per the general industrial practice. So generally, the standard industrial practice is what? Why this practice made? This practice made to reduce the cost, to cut the cost. So what they will do in the transformer, the we have the HV side and we have the LV side. LV side. The transformer is a bi-directional equipment. So we should tell the HV and LV side instead of telling primary and secondary side. Instead of telling this, we should tell HV and LV side. Because if I'm feeding power from this direction, so this would be my primary and this would be my secondary. Right? If I'm feeding power from this direction, so this is my primary and this is my secondary. So my primary, secondary, each and every time keep changing, but my voltage is not changing. So better word is used to HV side and LV side. Now coming to the topic. So when you are in the transformer, my HV side voltage, HV side voltage to LV side voltage, LV side voltage, this ratio, when this ratio is greater than 2, I mean that if I have a transformer which is 220 by 33, so if I divide 220 by 33, so this result will come more than 2, right? For sure. In that case, it is preferred to use a two winding type power transformer like this. Two winding type power transformer. Power transformer. At the same time, whenever my HV side voltage to LV side voltage, this ratio is less than 2. For example, I have a 220 by 132 kV substation. If you divide, this will come less than 2. In that case, we use a auto transformer. Auto transformer means like we can divide the transformer as a two winding how we can divide the, let us divide overall type of the transformer. So the transformer could be, if we divide this overall divide type of the transformer. So if anyone asking from you what is the type of the transformer, so generally we tell that as like oil cooled, air cooled. But the ideal reply should be type of the transformer is distribution transformer, power transformer, power transformer, and instrument transformer. Instrument transformer. So when any transformer dealing with the power which is rated into the kVA, so that kind of the transformer called as a distribution transformer, which is distributing power to the end consumers. Whenever any transformer handling the power or dealing the power which rating into the MVA, so this kind of the transformer called as the power transformer. And at the same time, when any transformer dealing with the power which is rated into VA, so this kind of the transformer called as the instrument transformer. The example of this instrument transformer is the current transformer and the voltage transformer, which ratings are burden are ratings we express in the VA unit. Like for example, 10 VA, 15 VA, 20 VA, like that. This all we will discuss in the CTVT sizing class. CTVT sizing, we will discuss about that VA calculations. Now, the next point, whenever this power transformer, again we can divide into this power transformer, again we can divide this all. I am dividing based on the use. Okay, based on the use, not based on the cooling medium, not like that, based on the application. Based on the applications, I have divided three. In subsystems, we use all three type transformer, all three. Here we use for the auxiliary supply, this is used for the power transmission purpose, this is used for the metering and protection purpose. So all three use in the substations. So again, this power transformer, we can divide into three parts. It could be a one winding transformer called as the auto transformer. It means in this particular transformer, we do not have two winding, we have a single winding. And to make the LV voltage, we are taking the tappings from the winding. So if I have a single winding, so what is the advantage? My all the winding is like in two winding we have the in like two winding we have a two set of the copper winding, but in single winding or in case of auto transformer, we have only one set of the copper winding core. So I'm able to reduce drastically the cost of the transformer, right? Second, this could be a two winding transformer, and two winding simple, just we have the HV side and then we have the LV side, right? If you see here in this, my cost approximately double, right, compared to this. And then we have a, I can say three winding, or I can say the multi winding transformer. The multi winding means we have the, when we have the two different set of source, in that case we go with the multi winding type transformer. The best example of multi winding transformer is the solar power plant or renewables power plant. In that, what we are doing, that we are taking the supply from different solar inverters, right? From different solar inverter, and we are feeding power to a common inverter duty transformer, ITT, different solar inverters, solar inverter, and we are feeding power to here, and this IDT collecting all, it could be 5 bonding like that, collecting power from all the separate solar inverter, combining all the power, and then providing one single output. Let us see this. If I go, let me check if I have a substations with, yeah, solar power plant. Could you see here, like inverter is not too much visible here. So this is a solar power plant. In this solar power plant, what we are doing, like we are making the ICR, inverter control room. We are making the module block. This is just terminology that we should remember, module block. And from this, generally 6.25 like megawatt or 6.5 megawatt one block we create, and of all this block power we are collecting through the inverter feed. Here we have a transformer. I don't think, is it visible to all of you? This is your inverter set. Could you see this? Could you see this? But this particular image, is this what I'm discussing here, this IDT. Here I have the inverter that I'm explaining here, inverters. And then here I have the inverter duty transformer. I think chat box is also on. Sorry, you can unmute and tell. If any engineer who don't have the background noise, it would be better that if he unmute and he responds. It is not clear, Amol, we are following the Google Earth coordinate. So you have to manage with the Google Earth coordinate. I will take up, if I have directly site photo, I will try to save this. But something is better than nothing, so that I can actually tell you that where we are using it. Okay, if I'm telling you just in a theoretical, so it would not be more relevant. If I'm telling theoretical, I'm explaining the same theoretical concept, taking the reference of the site, then it is more relevant. Okay, so for your information, your knowledge, you note down, this is my pin set. Below that, I have placed my central inverter. The participant who have background noise, never unmute their audio. The next time I'm not able to allow them in the class. Okay, yeah. Anyone, if working at the site, they could share the site photo directly. I'll try to open here. Anyway, coming back to the point. So here, what I do, that whenever we have more than 2 sources, then we go with this kind of the multi-winding transformer. Whenever we have the voltage which HV to LV ratio is greater than 2, then as a design engineer, I'm select this transformer, 2-winding transformer, and the company will tell this kind of the transformer as the power transformer in their work scope, power transformer. This is whenever my HV voltage to LV voltage ratio is less than 2. For example, in my case, 220 by 132 kV. So this is ratio is less than 2. Another example, if I take 400 kV divided by 220 kV, this ratio is again less than 2. If I divide it, just divide it. Okay. To be precise, let us divide this. To be precise, 400 kV divided by the 220 kV. This is ratio is 1.8. 1.8 is less than 2. So in that case, as a design engineer, we select the auto transformer or single winding transformer. Why I'm doing this? I'm just reducing the cost, cost, reducing. And you can see here, like here we have 2 set of the winding, here we have 1 set of the winding. So you're a lot of saving in your copper. a lot of saving in your insulation material, a lot of saving in your core, right? So each and everywhere, I'm just reducing the cost. So whenever the company have this kind of the system, they go with the Suraj, please do not touch your screen. Yeah, so here, uh, whenever this HV to LV ratio is less than 2, to reduce the cost, just okay. As a design engineer, as a company, we try to go with the single winding auto transformer, which is auto transformer. And if you see here, this topic I'm going to take in detail in my transformer module. So do not, uh, I'm not covering this transformer as of now. I'm just telling a brief idea about transformer. Again, this I'm going to take in 2 hour class. Miss the transformer is about 10-hour class. So I'm going to take this all things in the 10 hour session, not in the rest. As of now, you note down one sentence only. Remaining in the transformer module, we will discuss. So whenever, so now if you see here what I'm doing, that I'm taking the tapping. So it means my HV side voltage and LV side voltage is, if you see here, your HV to and LV is isolated, electrically isolated, right? Electrically isolated, magnetically coupled, but electrically isolated. It means like whatever the HV side harmonics coming, it will not going to LV side because it is not electrically connected. It is just magnetically coupled, right? So whenever I have a distribution loads, I have end users that may have the harmonics at that moment. I will try to go with this kind of the transformer. In my particular case, I have 220 by 33 kV. So this 33 kV could feed to some industrial loads, buildings. So there could be harmonics that may come from that industry to this transformer. So I do not want it to connect my LV to HV electrically, so that harmonics will not transfer. So in that case, it is good to go with the two winding transformer. But whenever I'm working on a grid substations and on the 400 kV side or the 220 kV side, there is no any industrial connection. This is all the grid connections. Grid connections means the chance of the harmonics is very less in this kind of connections, and working on the extra high voltage. So I have a choice that instead of going with the two winding, I can go with the one winding. I'm taking tappings from the windings only. So it means my 400 kV and 220 kV are electrically connected. Electrically connected. Am I correct on this electrically connected? It means when this electrically connected means my 400 kV substations and 220 kV substation is interconnected. Interconnected. So when my 400 kV substations is interconnected with 220 kV substations, in that case, the transformer which I'm using, this is single winding auto transformer. So the company will call this transformer, either they can call as the auto transformer or they can call as the interconnecting transformer. Both are the same. So here, if you see in this particular scope of the work, so this is the 400 kV by 220 kV. I'm going to use the auto transformer. Auto transformer is electrically interconnected. Due to this reason, this in this scope of the work, ICT word is written. In this scope of the work, the 400 kV and 220 kV and 33 kV is electrically isolated, and I'm using a simple two winding type power transformer. So due to that reason, here the power transformer word is written. Am I clear with the comparison between both scope of the work and the terminology for the transformer representations?
Yes, sir.
Thanks, brother. Thanks. So now, anyway, I am not finished transformer models. Okay, this is just give you idea about this and this. Okay, this all I'm going to take in a separate transformer module session, which is our module number 3. We are as of now, we are on module number 1, and we are discussing about the how to read the tender, and in that we are discussing how to read the scope of the work, and in that scope of the work, the terminology coming related to the transformer. Due to that reason, I took the transformer here. Okay. Now, another things, if you compare here in this scope of the work and this scope of the work, in this particular scope of the work, I'm using the reactor. I'm using the reactor. But in this scope of the work, there is no any reactor. Only like you see here, line and then transformer bay, transformer bus, power transformer, 33 kV line base. But here I'm using the reactor. So let us understand where we use reactor, where we don't use the reactor, and why we use the reactor in the extra high voltage substations. Okay, ICT bay means interconnecting transformer bay, means transformer bay. ICT bay means transformer bay in a simple word. Sorry, ICT bay means transformer bay. Why this bay is called as the ICT bay? Because they are using the single winding auto transformer, and HV and LV is electrically connected. Electrically connected means interconnected transformer. Means they will use interconnecting transformer here. Now coming back to the reactor. As of now, I'm discussing the scope of the work only. I'm taking different example of the scope of the work of different voltage level. So if you will work on this kind of the voltage level, which is 400 by 220 kV, so out of 10 project, in your 7-8 project, you have to use the reactors. Particularly if you're working in Asian country like in India, China, who have a large geographical regions, most of the time you have to use the reactor in the substations. So let us understand about the reactor and then reactor. The reactor bay means the reactor is connecting to your bus bar, so that connecting bay is called as the reactor bay. This is just the simple things. So here I'm using 2 reactor of 125 ampere. Reactor rating comes into var. The transformer rating comes into MVA. Okay, so please note down the difference in that. Here if you see ICT 4 by 220 kV, 500 MVA, and here MVAR. So 2 number of reactors, due to the reason here 2 number of the reactor bay. So let us come on the reactor now. Come on the reactor now. The reactor we use in the grid substations. Capacitors we use mostly in the distribution substations, because the distribution substations is connected to a industry, and in that industry we have maximum inductive load, like motor is your inductive load, for example. So industry we have maximum inductive load. So in order to counterbalance the inductive load, the distribution substations have the capacitor, since they are in their uh, distribution substations. Whereas in case of in case of the ultra high voltage or extra high voltage substations, they have the reactor in their substations. The reactor is nothing, just an inductor. So inductor called as the reactor. So in today class D4, I'm taking the reactor. So in project scope of the work, the reactor is mentioned. So let us understand why reactor are used in the substations and why reactor have used in this particular scope of the work for 400 kV and 220 kV substations. So before understanding about the reactor, let us understand about the transmission line, and then we will come on the reactor, because reactor is related to your transmission line length and voltage level. So let us start with the transmission line, and then we'll come on the reactor. So before us understanding the reactor, let us see the transmission line representation. So any piece of the any transmission line which is connecting a substation to the another substation that transmission line we can represent by 4 parameters, the electrical parameters. This is how this could be represented. Let me check if I have any Google Earth coordinate that is indicating the transmission line. Abhijit, please mute. Okay, it's not indicated here. 405. I just want to take a side photo of the transmission towers are line. Which could you see here the towers? This tower here, the next tower here. It is not crystal clear visible, but I hope you can see one tower here, next tower here. Similarly, next tower here. Is it visible? Could you
Yes,
guess?
sir, yes, sir.
Yeah.
Shadow is
So-
shadow is there.
Yeah. So this transmission tower circuit we can represent like in the electrical parameters we can represent like this. This line can be represented by 4 electrical parameters, which is resistance, which is very less, resistance, inductance L, which is high compared to the resistance R, capacitance, which is more high than inductance L, and the shunt conductance G. So these parameters are uniformly distributed along the transmission line length. Hence, it is called as the distributed parameter of the transmission line, and air between the line conductor and the ground work as a dielectric medium between the line and the ground. So now, what will happen whenever the condition is that whenever we have a longer transmission line word is important. The short transmission line, if we have, then reactor will not come into the use. It will not come into the use. So whenever we have a long transmission lines, longer line length, then higher the effect of the distributed shunt capacitance. And in the case of, this is the next word is also important. In the case of less loading, a lightly loaded condition means when your loading is less, so your resistance and inductance component would be less compared to the line capacitive component, right? The shunt capacitance C between line and ground, there is no any physical capacitance, means do not assume that the C you could not see here. There is no any physical C, but like the line and ground will form a virtual C. So do not think that you are putting the plate and this kind of the physical C. It will form kind of the virtual C. So between the capacitance less than the capacitive component, the shunt capacitance, between less loaded or lightly loaded conditions, the resistance or inductance component would be less than the capacitive component. The shunt capacitance C between line and ground inject, this is important word, inject or generate huge reactive power into the grid system, and current flowing over long transmission line have higher. Due to this reactive power, there is some line impedance, and here I'm injecting the power, right? So due to that reason, the current will flow, and that current will be a capacitive component. So this cause a voltage, this huge reactive power injected by the capacitance will cause a voltage increase at the receiving end substation, and the result is known as the Ferranti effect that we have studied during the college time. The Ferranti effect. Let us simulate this through the ETAP. Through the ETAP. So far, what I am telling this sentence only, I'm now explaining through the ETAP now. So let us take a line. First let us take a grid here, right? And let us take a bus bar. Let us take a bus bar. Let me connect this bus bar. I'm trying to explain the Ferranti effect. I'm trying to explain you my theoretical statement. In that, I'm telling you capacitance, the shunt capacitance will inject reactive power. So this statement I'm trying to simulate here with help of the ETAP software. So I'm taking the, as I told, this is high voltage, long transmission line, and the higher voltage also. Long transmission line and higher voltage. So let us take, this is my 400 kV bus bar, and this is again 400 kV grid, right? And I connect this grid to this bus bar. So this piece, this is my sending end substation. Sending end substations, okay? Sending end substations. And now I'm taking a bus bar, which is here. Again, I'm taking as a 400 kV bus bar. And this is my receiving end substations. So I can like take a similar kind of the box here. And I can tell that this is sending. So SENDIN, sending, SS, sending substations, right? And this is I'm telling as the receiving substation, right? And between both the substations, I have connected a transmission line for the power transmission. So this symbol is indicating line. So just click here and so it is selected. So just put here, and after that, one end of the line to the sending substations, another end of the line to the receiving substations. I connected here. Now I told you longer transmission line. So I'm just double click on this transmission line. Then line editor block will open here. So my sentence here, long length kilometer unit. There is like foot, mile, meter, kilometer. So go with the kilometer. I'm putting here any 350 kilometer line, which is considered as a long transmission line, right? This is line. And then I go to the parameters, and here I selected a conductor. So there is two options. First options, like we can select a library. We can select a conductor from its own library. Another options, we can go with impedance, and here I can click on the user defined, and in the user defined I can manually put the resistance of the transmission line, reactance, and the admittance of this transmission line. Manually I can put here. So when we do the real-time project, so we do not go with these parameters. We go here and we take the like these parameters, the transmission line parameter, this POS, any G and 0, it is telling the positive sequence, negative sequence, and zero sequence. So in case of the static equipment, line is my static equipment, motor is my dynamic equipment. So in case of the static piece of electrical equipment, my positive and negative component, symmetrical component, is identical and similar. So what value I'm putting here, same I will put here in the negative also, just copy paste. So positive, negative, similar. Zero component would be approximately 3 times higher than the positive components. So this is one piece. Make sure you click on the user defined. Another case, I don't have as of now any transmission and conductor technical parameters, so I don't have any resistance and reactance value here. And if you see here, base T1, base T2 means the T1, this resistance and the T1 temperature. Because if your temperature will change, your resistance will change. So this is I'm putting on 75 degrees Celsius temperature. So I can see that parameters and what temperature written in the conductor technical data sheet that I select here, and then I put the value here. So as of now, I don't have any. So I'm selecting a conductor from ETAP itself library just for my simulations purpose of the concept. Okay. So I select any parameters. So I'm taking this conductor gold size is 431 square meter, 54 is found in this particular conductor. So I'm click on the OK. So if I'm putting on the OK, and then you go to the impedance, you will see okay, nothing here. So let me put the configurations. So here parameters which I selected, and then here I need to put the transmission line or transmission tower height from above the ground. So I'm taking a 24 meter because for the 400 kV tower comes in the generally in height of 24 meters. So A, B, C means A, R, Y, B. So R2Y, Y2B, this is spacing of the phase conductor. So I'm taking as a 6 meter for an example. Generally in 400 kV we take in this range, and then let us see the resistance. Yeah, so resistance you can see some default value coming here, calculated value based on this parameters and the configurations. This impedance is taken here. Another options we can click on user define, and then we can put the real value here. So just this, I put the line length, which is 350 kilometers, and I put the line impedance parameters, which I told you that transmission line is represented by this here, so that I put in the ETAP now. Okay, and then if I perform a PQ means this P is active power, Q is reactive power. So I perform the load flow analysis or power flow analysis. In this analysis, I just wanted to check how much active and reactive power is flow through the circuit. This is what I wanted to see. All your query note down on a separate pen and paper, and the last unmute and discuss one-to-one. Okay, Imran, just know with all of you, because when you put anything, it pop-ups and then it disturb my flow. And like I concentrate what is coming on the chat box. This is the one request. So my request would be 9 to 11 my time. No one will disturb me. I will try to cover each and everything. I'm not going to skip anything. I hope in my 12, 15 years classes, you have realized that I'm not in the rush to finish the syllabus. So I'm not going to skip anything. But the case that you will not disturb my flow. Note down on a separate pen and paper. Okay, Imran, just do whatever, like, and when I'm telling that, is it okay or not? So I have another request that any participant just unmute, and then they can acknowledge whether it is visible or not visible. Okay. Yeah. So now I have modeled this piece of circuit on the ETAP, and now I'm going to check the power flow. As I told you here, as I coming back to again, in case of long transmission line, which I took 350 kilometer longer line length, then effect of distribution capacitance higher. In case of less loading, so I'm not going to connect any load here. So it means this receiving substation is less loaded or not loaded. This is also important, less loaded or light load conditions. The shunt capacitance inject huge reactive power in the system, and current flow over long transmission line have higher capacitive components. And this causes a voltage increase at the receiving end substations, and the result is known as the Faraday effect. So just taking this, click on this P and Q. After you click this pencil, which is now in the edit mode, it go to the run mode. Run mode means you can't edit anything. There is no any equipment symbol you can see on the right hand side. So again, next you click on the P and Q run load flow. You click on the run load flow. Then you can see here what is the result. Let me check this. Now I wanted to change the unit, result unit, because this unit is large. So go on the display options. You click on the kVA into MVA, and you click on, my concern to see the power flow result into active and reactive power. So I click on the megawatt and ampere. right? And let me click on the angle also. One important thing that I'm going to explain. Length is important. Other thing is not important as of now for me. So I like uncheck these boxes and then click OK, because I just wanted to show that what line length is here. Now let me check this voltage percentage, unit in percentage 2 into kV, so that I can check the value directly in the unit, not in the percentage increased. So what is the result we can see here? What is the result? You see here, from sending substation, I have connected a sending substation to a receiving substation. There is no load connected to the receiving substations, right? Even though 1.4 megawatt power is indicating, which is flowing. At the same time, what is the, so this 1.4 megawatt plus 161.7 megawatt, what is the meaning? This is P plus Q right now, the active power plus reactive power. And if you notice here, your active power is 1.4 megawatt. Let me take the snapshots to understand the ETAP result in the detail. Just 1 second. Yeah. So here, if you observe the result, how much I'm sending here, 400 kV. How much I'm getting here, 430 kV, right? Here, like when we discuss any concept, any engineer who can unmute and we can have correspondence.
Yes, sir. Yes, sir.
The engineer who don't have the background noise, this is the conditions when you unmute yourself. Krishnan, yeah. So Krishnan,
Yes, yes, you are right.
I'm sending 400 kV,
430.
but I'm getting 430 kV, right? Is it good
Higher,
or bad?
yes, higher voltage.
So it is
See,
good for or bad for the system? It is good.
Bad.
bad.
Why it is bad? Because your system is designed for 400 kV only, right?
Yes,
Yes.
Your all equipment, breaker, CTVT, transformer, each and everything that you have designed for the 400 kV rated voltage. But at the same time, you are feeding those equipment to 430 kV. It means the equipment insulation may damage, equipment may damage due to higher voltage stress. So it is bad, right?
Yes.
Because your design in your home house, you can take, you have 230 voltage. If 400 voltage come on your house, so what will happen? Your fan, TV, like
Yeah.
light, each and everything
damage.
damage, blast, right? So
Yes.
it is not good to feed more voltage continuously than your design voltage. So it is bad. So we should emit this, we should avoid this, we should reduce this. This is the one thing. So this effect I'm telling as the Ferranti effect, and who, why it is happened? Due to the longer length of transmission line, and this line is not connected to the load. So this is why this is happening here. Another point, coming to the ETAP result, if you see here the result, it is indicating 1.4 megawatt and then 161.7 MVAR. This is negative. So you try to understand, this is 1.4 megawatt P plus JQ, and your Q is minus 161.7 megawatt. This is your reactive power, which is P. This is your reactive power, which is 161.7 MVAR, and this is reactive power, so it will come into a MVAR unit for sure, which is P plus JQ. P plus JQ. So your Q is reactive power, which is coming 161.7. Now you see the direction. So 1.4 megawatt is flowing through this circuit, right? But at the same time, this reactive power coming into negative sign. When the negative sign comes, it means this power I'm not withdrawing, I'm not withdraw or taking or consuming from the grid. I'm reverse, means I'm injecting to the grid. I'm feeding to the grid. So if anything which I'm feeding injecting to grid, so that unit will come with negative sign. Am I clear with the sign?
Yes, sir.
Okay, sir.
Hello? Yes, clear.
This negative sign means I'm injecting this negative.
Hello?
Yes.
Sir, in general conventions, in inflow of these parameters taken as negative, basically. Outflow is positive.
Yeah, flow is positive. And if anything, that I'm reverse injecting, okay, to the grid. So that symbol comes into the negative. If I'm injecting, I'm generating, which is generated by this line, so it comes into the negative. It means this particular system is, now let me make this squeeze.
No, sorry, you're not understood. Actually, if I'm injecting reactive power, then it is a positive. And if I am
Injecting,
taking from the
injecting means negative, taking means
outflow.
positive.
Outflow is positive and inflow is negative.
Yeah, inflow is negative. So this transmission line is generating or injecting 161.7 megawatt power to the grid system. Okay. Am I clear with negative sign?
Yes, sir.
Yes.
Okay. So from this understanding, from these simulations, we develop another understanding. What is my another?
Can you please repeat the sign, sir, once again, please?
Please focus to my sentence and pay your 200% attention. The time is very
sure.
important.
Yeah.
Okay. Yeah. So one more thing, that could you see here? There is two kind of power flow. One is the active power flow and one is the reactive power flow. So could you see here the voltage and their voltage angle?
Yes, sir.
So the active power flow from higher voltage angle to the lower voltage angle. 0.9, this 0.97 means minus 0.97, minus 0.97 is lower voltage angle compared to the 0 degree, right?
Yeah.
So active power flow, this is very important statement. Active power flow from higher voltage angle to the lower voltage angle. Reactive power flows from higher voltage magnitude to lower voltage magnitude. So reactive power is flowing from this 431.1 kV from this towards the 400 kV, and again it is flowing into the grid as well. So we discussed two things important concept.
Hello?
By covering the reactor here.
Hello?
Yes.
Sir, you have used the negative sign for this reactive power also at this station. That is
Reactive power injected by the transmission line into the grid system. So that is why I use the negative sign for that. Okay. Hello.
no, actually, you have negative sign at both the substations. Receiving and
negative sign here. This negative sign.
no, this one, no, minus 161 at the receiving end and minus 161 at
This
the
is all
sending end.
this all power flow in the reverse direction. So it is negative here as well, and it is flowing towards the grid. This all is flowing from receiving substation towards the sending substations and towards the grid till here. If you double click your grid, you can see how the grid is operating. Could you see the operation of your grid? This is operating at 1.4 megawatt and operating as minus 161, right? Could you see my grid editor?
Yes, sir.
How it is
Yes, sir.
operating?
Yes.
Okay. So now what I'm doing,
Sir,
this-
can we consider like this 161 reactive power generated by transmission line, and
yes,
since it is flowing opposite side at the both the end, hence we are considering negative?
yes, it is flowing from, it is flowing towards the grid, so negative sign.
Okay.
Towards the grid.
Okay, clear.
Okay. Now, as I told that if I have long transmission line, then it is having this voltage increase. Let me now change the length of the transmission line. If I just took 100 kilometer, means I took a medium transmission line, not long transmission line, 100 kilometer length. And then let us do the same simulations again, and then let us see the result in the voltage. Could you see here the result? It is 402 only now. Initially it was 430.
Yes, sir.
Means if your transmission line is short, so don't bother about the reactive power. Okay.
Hello.
Yes.
Hello. Sir, there is a little confusion. Actually, MBR is the same at both the substations. So
Yeah.
actually,
Yeah. So means from higher voltage
Actually,
to lower voltage,
yeah,
my
yes, that's fine, but
44.6. Note down, no, sorry, we'll discuss later on in the lab.
okay.
Class.
Okay.
Note down. Okay. Here I don't have any source. I have source here. This from here to here, this is a transmission line, and from sending substations to the receiving from receiving substation towards the sending substation, I'm sending the power. Could you see that now grid operated at minus 44.646 means I'm not taking power from the grid, I'm injecting power into the grid. Okay. At this point, minus 44.664 MVR, we have the power which is generated by the shunt capacitance. Okay. Now, so therefore the shunt reactors. Now this is the theory here. This is the simulations here. Then how to mitigate this 430 kV. So therefore the shunt reactors are used inside the substations to compensate the reactive power generated by the shunt capacitance of the long transmission line. So therefore the shunt reactors, which is a reactors with inductor. Shunt reactor or inductor work as an absorber of the capacitive reactive power. The reactive power generated by the line capacitance is consumed by the inductance of the shunt reactor, which is used in the substations, therefore increasing the reactive power transfer capacity, and reactor are also utilized to regulate the voltage regulations at the receiving end substations in busbar during the light load conditions. So now what I'm doing is, let us take the shunt reactor in the substation. So how we take the shunt reactor? We don't have the shunt reactor in this ETAP. So what we do, we take is a static load. In here we have the loads. So like here we have the source. So for the source we have the grid and we have the generators. After that we have the load. In the load we have this wind turbine is also generator. PV is also generator. So here we have the induction machines and synchronous machines, lump load, wall, static load. I will come on the load flow analysis that I will discuss the difference between lump load and the static load. Lump load is a combination of a static and dynamic load. Dynamic load means the rotating load called as the dynamic load. So the lump load is a combination of a static plus dynamic load. Means in any industry we have some static loads, means any power electronics device, any device which don't have any mode rotating part. So when we combine both the static loads and the rotating load, so that kind of load altogether called as the lump load in the combinations. And when we have only static loads, means nothing, we don't have any motorized rotating load, so that load called as the static load here. So I'm taking a static load symbol from this. and this I'm indicating as my reactor in the substations. So now I'm just connecting a reactor in the substations at the receiving end substations. This reactor is indicated by a static load, and the reactor rating comes into MVAR, right? So now this load rating I'm expressing into MVAR unit. Just 1 second. In my system, I don't have the space. So here, if you see ratings, so info, the load name, all these things we can put here, and then going to loading. So ratings, kV, MVA, megawatt, MVAR, power factor, and this all things. So I'm taking this unit into MVAR. And by the chance, suppose I'm taking this unit in as of now 80 MVAR, right? Nothing any megawatt, so that I can tell MVAR as a reactor rating. And now let us again perform the same power flow analysis. Could we see here the result? Initially, how much it was for 350 kilometer, 430 kV, right? Without reactor here.
Yes, sir. Yes, sir.
Without reactor here. Once I put the reactor, this is 399 point, which is very close to the 400 kV, right? I took the 80 megawatt. You can go and here you can play. Let us select 81 megawatt. Click on the OK. Then again perform the load flow 398.9. So just like that we can simulate precisely 78 MVAR to reach till 400 kV. Yeah. So if I took 78 MVAR precisely, the result is just 400 kVA, which is required, right? So now coming to here, therefore shunt reactor are used in the side of the substations to compensate the reactive power generated by the shunt capacitance of the long transmission line. And shunt reactor work as an absorber of the capacitive reactive power. The reactive power generated by the line capacitance consumed by the inductance of the shunt reactors used in the substations. Therefore, increasing the active power transfer capacitor, reactors utilized to regulate the voltage, which is regulated. You can see in this earlier it was 430 kV, now it is 400 kV. So it regulates the voltage at the receiving end bus bar during the light load conditions. Am I clear with this page and with the ETAP simulations?
Yes, sir.
Now, why this is planned? Why this is planned? What I have told here, this all things I have mentioned in the presentations as well. So let us model a transmission line using ETAP. So here we are taking 350 kilometers for long connected from sending substations to the receiving substations. Let us assume no load connected to the receiving end substations. But after doing the load analysis, the below result came. So 2.16 megawatt real active power flowing from sending substations to the receiving substations. So it is real power loss, and minus in this particular result was 199.9 megawatt MVAR. Power is generated by the transmission line and injected into the grid system. Therefore, it appears with negative sign, and this is injected power by the capacitance of the line. So here we need to note an important concept that active or real power flows from higher voltage angle to lower voltage angle, and reactive power flows from higher voltage magnitude to lower voltage magnitude. So 199.9 MVAR power flowing into grid system. Due to that reason, it is appearing in negative sign here and here everywhere. So here, the shunt reactor can be represented as a static load in ETAP, and the rating should be in AMBA. So after connecting a shunt reactor, the voltage value was reduced from 430 kV to 400 kV, which is near to the rated voltage level. So here we can say that the shunt reactor is used in substations to consume the capacitive reactive power generated by the shunt capacitance of time and regulate the bus voltage near to required rated voltage. The typical shunt reactor rating are 50 MVAR, 63 MVAR, 90 MVAR, 120 or 125 MVAR, and that precisely can be calculated by doing a system study considering the real-time line impedance, the real-time line length, the real-time line conductor height above the ground, and precisely we can calculate what should be my rating of the reactive power. But now you can see one thing here, that why reactor rating coming in this range 50, 63, 90, 125. How this kind of ranges we are taking? Not why not taking same 400 MR or 200 MR? Why not taking? Why this range of this kind of range I'm taking? And what should be the precise values, so that we can obviously calculate by putting the real time parameters of the line. So here we can understand the briefly about the reactor rating calculations as well. So now one important thing, when any company create the new substations, so they plan the substation life for the how much year generally they plan the substation life? How much year?
30 to 35 years.
30 to 35
35.
years. 35 years, 40 years, whatever you can say. 35 years. 35 years life they are planning means, and when the substation and transmission system is new, so at that moment the entire transmission line and substation is not 100% utilized, right? When it is new in first year, right? Now, am I correct?
Yes, sir.
Yes, sir.
In the second year again it is not 100% utilized. In third year again it is not 100% utilized. Means initially it is underrated. Underrated means, like if you take example, in India we have developed the infrastructure for 1200 kV, but I'm not operating the system on 1200 kV. The same infrastructure I'm operating at 765 kV as of now, right? And this is another example. So what I'm telling, that whatever the infrastructure I'm making, a government is making, so they are not utilizing whole infrastructure at their full capacity. Means in the early days of their system, this entire system will operate on 25%, 30%. Means I can say it will operate on light load condition. Light load or less load conditions it will operate. Less load conditions it will operate. So when they're operating at light load or less loading conditions, then at that moment your reactor is important in the substations. But later on when this substation is operated at their 80% or 100% capacity, then we can switch off this reactor, or we can take service out of this reactor. Right? So due to that purpose, when we connect a reactor, we connect this reactor by using a particular circuit, having the dedicated breaker, CT, disconnector, and so whenever we require, we can isolate or switch in or switch out. But early days we take this as in the service in conditions, switch in conditions. And one more thing, that in the transmission line, in a particular substations, there is a common bus bar, and there are too many transmission line base coming from sending and in connecting to the receiving substations. So now here I have the two choice. I can connect this reactor. The reactor symbol, you know that this is inductor. So this symbol that we use, this is just like a inductor, this kind of the symbol L. Rating in MVAR, this symbol we use. So this reactor, I can connect with bus bar. This is option 1. Option 2, if there is only one transmission line, which is longer transmission line, suppose 350 kilometer, 400 kilometer, but rest other transmission line is short transmission line, which is connecting the nearby substations. That could be the case that I'm taking a transmission line in from the very remote substations, and then I'm taking the outer circuit out, line out, I'm connecting a nearby substations to feed a nearby geographical region. So the remaining line could be short length. Only one particular line could be the longer length. So in that case, I can connect this reactor instead of connecting on this bus bar. I can connect in parallel of this line bay. And since this reactor is connecting in the parallel of the line bay, I cannot connect into the series. Note down, because if I connect into the series, how I will isolate in the future, right now? So I have to connect this reactor into the parallel. Since I'm connecting into the parallel, due to this reason, we call this is shunt, right? And since parallel connections, so one phase, one terminal on the line side, and the next terminal would be connected to the ground side. Then only it will form the parallel connection, right?
Yes, sir.
So this two choice we have. Either we can connect with the line, or either we can connect with the bus. So suppose we have many transmission line, and all the transmission line, we can see that this is longer transmission line. So instead of putting the reactor on with each line bay, I'm going to take one common reactor I will place on the bus bar only. But I can see that I have only one particular line length higher, but other length is not so much longer length. So, and then I will connect directly with that particular circuit only, instead of putting the reactor on the bus. But anyway, this all decision is not taken by the design engineer. This all decision is taken by the system planning team. System planning team or transmission line planning team are the power evacuations planning team. There is a separate department who do this kind of the planning, and based on that, they mention the scope of the work in the technical specification. So when the project coming into the market, before that, this all feasibility study have been done. So I will follow as per the scope of the work, but I'm telling you, this is like if you are working in an owner company, developer company, and you have to plan like that. So how you will think like we have a few engineers from the government utility. So for that purpose only. Okay. Am I clear with the so far? Why reactor in this particular?
Yes, sir.
For reactor,
Is given.
just one point for reactor, it compensates the reactive power. It also take care of angle because you are talking about the angle also.
I'm telling the angle. This is just reference angle of the bus voltage. It will not going to do it with angle.
Okay.
Coming back to the discussion why the reactor have been used. So anyway, so far I'm clear why reactor use here. So reactor used to compensate because here we have the longer line length, line by 2 number, and both line by could be the longer line length, so that to compensate the capacitive reactive power, this particular substance require the reactor, and they are putting the reactor, they are connecting the reactor to their bus bar. So that is reason they are calling this reactor as a bus reactor. If I'm putting the reactor, connecting the reactor into the line, then I will call this reactor as a line shunt reactor. Please note down that word as well, terminology of the wording as well. So bus means connecting on the bus. If I'm putting the line shunt reactor, it means it will connect a particular dedicated line. And on which line it will connect, that we have to check with the owner, with the client, that on which line you require the reactor connections, the shunt reactor connections. Coming back to the reactor connections, so as I told that reactor could be connected. There are two type of the shunt reactor connection possible in the substations. Line shunt reactor means reactor connected in shunt of a transmission line, or the bus bar shunt reactor means reactor connected in shunt of the common bus bar. Transmission line shunt reactor can be Now, as I told that it could be switchable or not switchable. So transmission line shunt reactor can be conventional with constant inductance or control with variable inductance. And for the controlling the reactor, it can be made switchable by connecting through a dedicated circuit breaker. The shunt reactor connected with transmission. Now, the next important concept. Whenever the shunt reactor which is connected with the transmission line, in shunt of the transmission line, not on the bus bar, in the shunt of the transmission line, so that reactor must have the neutral grounding reactor NGR. But why I'm telling this specifically here, because I was executing one project. In that project, the client working a project in Uzbekistan, they have not mentioned in the scope of the work about the line neutral reactor when they release the scope of the work. There's a company called Aqua Power. I hope if you have heard that company name, Aqua Power. So the Aqua Power is making the substations in Uzbekistan. They released one scope of the work for the designing of the substations, which is 500 kV substation. And now they didn't mention about the line grounding reactor in the scope of the work. And later on, once the system is ready, then all of a sudden, the NGR requirement came into the picture. So the company realized that this should be mentioned in the scope of the work, but by mistake they did not mention in the scope of the work, and they were not aware about this neutral grounding reactor requirement. So due to that reason, I took this NGR dedicatedly in this discussion, so that whenever you work with, you deal with the reactors and that reactor connecting with the line, you keep in your mind that neutral grounding reactor. Another piece of equipment would be required in the substations. Why it is required, I will tell on this. I will come on this. So the shunt reactor connected with the transmission line needs to be provided with a neutral grounding reactor NGR. So which is connected between the neutral bushing of the shunt reactor and the ground. Why? To facilitate the single pole auto reclosing in the circuit breaker. However, in the case of the bus reactor, neutral is solidly grounded and the NGR is not required in case of the bus reactor. I took this statement. What is my reference of this statement? So first of all, let me show you the drawing, the SLD, and then I will come on the statement. So if you see here, this is my 500 kV transmission line. Could you see here? The bus bar I deleted here because I just wanted to focus on the line reactor. Means if I take the entire picture, so the entire picture like would be one, it's common bus bar, so means I can draw a breaker. I could not indicate it here, so like I can draw the CT and then breaker, and then again one disconnector here, again one disconnector here. I will come on the reactor part, this SLD part later on, and there is a common bus bar, bus bar. This is my 500 kV transmission line, and I took, so in this 500 kV transmission line, we have the first surge arrestor. I will come this all equipment sequence in my next module. This is my, as I told in the beginning about the carrier communications. So for that, I have coupling capacitors. And this is coupling capacitors. Here I have line matching unit, LMU, and here I have the power line carrier communications. This is utilized for the carrier communications of the two substations. I will come this part later on. And third equipment is my wave trap. Wave trap is again inductor, so that's why inductor is indicated here, wave trap. And then we have the CVT, which is utilized for the metering and protection purpose. Then I have dedicated metering CTVT for the energy metering or tariff metering of this particular dedicated feeder. Due to that reason, this EMBT and the CT is coming here. I will take this part separately. And then I have the disconnectors here. This earthing switch for the line maintenance, and here I have disconnected. And then I'm taking tappings from this conductor, and then I'm connecting here the reactor, which is, you can see here, LR line reactor. This is my reactor here that we discussed, and it is connected with help of the disconnector earthing switch, because we require the maintenance of this breaker. Due to that reason, this is the breaker here, circuit breaker here. I'm using circuit breaker. Why? Because I wanted to make this reactor as a switchable reactor, right? So whenever I require to switch on the reactor in the system, I can close the circuit breaker. Whenever my system is running on the full capacity, I don't require the reactor, so I can switch off this reactor. So to make it switchable, I use the dedicated circuit breaker here. The circuit breaker must have this controlled switching device. I will take up this control switching device in the breaker topic. What is control switching device? CST. When it is required, when it is not required. So when I require the precise switching and for the dedicated circuit, so at that time, along with the breaker, we use some devices. So this is one device, control switching device. I will take this point with breaker modules, CST, so that I can get the point on wave switching, which CST will provide. And then after we have to do the protection of this reactor. Due to that reason, we are using this surge resistor here. And this is my reactor boosting current transformer. Due to that, it is indicated like a boosting current transformer, which is utilized with the reactor boostings to get the protection of this reactor. For the reactor, we require the differential, overall differential, and overcurrent earthfall protections in the backup. So all the protections will get with help of this CT, which is connected with the reactor. And then here this reactor part finished. So after the reactor, again we have connected the surge resistor again. And after that, if you see, I have used NGR here. Do not confuse NGR as a neutral grounding resistance, because there is one more NGR in the electrical system, which is neutral grounding resistor. But in case of substation, when this reactor is connected, NGR is connected with the reactor, then it is not the neutral grounding resistance. It is called the neutral grounding reactor, NGR, neutral grounding reactor, which is I'm connecting with the in series of the reactor, and then it is going with the earth. So this is how the concept we represent through the single line diagram. And now coming back, that why reactor is required. Coming back, sorry, why NGR is required. This is when we have line reactor. Whenever I have the bus reactor, if you see, this is my circuit diagram for the bus reactor. So just bus bar and then breakers, disconnector breaker with CST and then CT and then disconnector, and going, taking circuit out, and then isolators or disconnectors, earthing switch directly connected to the shunt reactor here, and then it is connected to the ground. There is no any NGR coming here, right? So for this NGR, why it is required, there is two things that we should refer. The first things that I took the reference of the IEC 60076 part number 6, page number 97. I have the entire space IEC. So go with the IEC. IEC 60076 is the standard for the power transformer. Reactor comes in the family of the transformer. Due to that reason, this 60076 is applicable for the reactor also. And in this 60076, there are too many parts. Dedicated part number 6 will utilize for the reactor purpose. So please memorize this standard name and part name 6 for the reactor. And now, if this is 246 page, so I am telling go to the directly to the page number 94, 97. So when I read entirely this standard, when I read in this standard, go to the 95 and 96 and 97. So when I come here, This is the important when I have read the standards. So you see here, shunt reactor for lines, which is in our case with single pole auto reclosing. So this standard directly telling you require the NGR. Shunt reactors connected to a line are grid with an effectively earth neutral are normally at the reactor neutral. In some cases, the transmission system where the line has single pole auto reclosing. What is single pole? What is three pole? What is auto reclosing? This topic I will take in the breaker module. So as of now, please note down the concept. You put the star, and this reclosing we will cover in the breaker model. Or it would be better if you can check through Google and note down as of now. But if you could not note down, then I'm going to cover the auto reclosing. Okay, means it related to the fault. Most of the fault is like temporary fault, so no need to close the system permanently. We can close temporarily. We can open the system and we can reclose. So that reclosing called as the auto reclosing. So this auto reclosing done by auto reclose relay. So a system where the line has single pole auto reclosing installed, it may be preferable to control the secondary arc current and transient recovery voltage for single line to earth fault. This may be done by either adding a neutral reactor to connect the shunt reactor. This is the recommendation coming from this IC standard. Shunt reactor neutral to earth path are by open neutral with suitably rated such as the protections. Both methods require a higher insulation level at the shunt reactor neutral to meet the temporary or voltage requirement during unbalanced conditions. Because you are doing single pole auto reclosing, so unbalance will come. This is IC standard, which is directly telling you. But if you wanted to develop your full knowledge, so I'm not going to like cover the theoretical part, but I can tell you the best research paper that you can go through and you can develop your understanding. I wanted to be specific on the project more compared to any theoretical discussions. So if you see here, this is guidelines for selection of neutral reactor rating for shunt compensated. So in this guideline, you can also calculate the rating as well. Guideline for selection of neutral reactor rating, NGR, neutral grounding reactor rating for shunt compensated extra high voltage transmission line. This is by the PRDC. These are the engineers who have published this research paper. So please, I will share this in the WhatsApp group. Like you can 6-page document. Go through this document. It will give you what is single pole auto reclosing, why it is emitted by connecting the neutral grounding reactors. Okay. So I will share this theoretical. Go through and develop your understanding. This is another that also I will share with about the like react. Here you can find out the reactor rating as well by putting some formula for that. Okay. So this 2 research paper, this is IC which are telling. So this is how we are following the standard in terms of the drawing here. Am I clear with the reactors? Am I clear with the reactor, which is mentioned in the scope of the work here? Type of the reactor connections, and when I'm connecting the reactor on the line, we require the neutral grounding reactor. It is recommended by the standards, and there are several research papers also on that. So in my now let us take the next step for the technical specifications. So what I'm doing, let me come back. So what I'm doing, I'm discussing how to read a project technical specifications. So I discussed the first, you will check the scope of the work as a design engineer. Then you will check what is the list of the document and the calculations are list of the deliverables that you have to prepare. List of the documents documents could be the drawing and the calculations, so that you will collect from the EPM, your engineering project manager or the client. Third, we discuss about that, yeah, after scope of the work and document, you have to read the technical specification of the project, the bid technical clarifications. Then you should know about the grid requirement when you are designing, and plus you should know what is the IEC and IEEE standards and what is their guideline. And in this case, as we discussed, that if I know the standards, so I can say that the NGR required with the reactor. Right, this is my step 3. Fourth step, when we start any project reading, that we will study we will go through what is the site conditions, site environmental geographical conditions. Why? Because the occupied area, since the occupied area by substation is large, they are covering a large area. Like here you can also see, like they are covering a large geographical area to make the substations here that you can see here. So whatever the site environmental condition, that will also affect on your system designing. So make sure whatever the equipment you are purchasing, whatever the calculations you are doing, you are following that particular site site data or site environmental data also during your equipment procurement, during your calculations, each and everything. So that will also we have to check. Therefore, for the design of the substations and equipment selection, because equipment rating will depend on the site conditions, so equipment selections, it is important. We should consider not only the electrical parameters but also the environmental conditions where the substation is to be placed. So go and check that in this specifications where is my site conditions given, and then note down that site conditions. Note down that site conditions. And if it is not given, then you ask your project manager or your client to provide you the site conditions. What is the site ambient temperature? What is the rainfall? Each and everything you have to make sure it is written. It is written. So go, this all is your, okay, here general conditions contract. So it is not, your commercial department will see the contract conditions. For us is the technical clarifications, technical specifications. This important claims, payment, these all things, delay, penalty, this is all your commercial things. So you just emit that page. Payment terms, wages, this all, no need to go through this all, you just pass this, because it is the responsibility of your this project team, procurement team. They will work on this. As a design engineer, you will not work on this. Okay, so I just wanted to check what is the specification started. So part 1 technical specifications, volume 2 section 1 project. Okay, this is my scope section. So on 1800 page directly I came on page number 266, and here my technical specifications given. So this is part 1, part 2, because in this case we have the line, so that line is coming on the part 2. Okay, and then detail of residential quarters. Okay, description they have given of the bay, and then check where your site conditions. Here you can see your fault level is given. So when you are designing, you will make sure for the 220 kV 40 kilo per fault current, for 33 kV 25 kilo for the same fault current. Okay, so one thing that you check your fault rating here. I will take this fault rating in my next class. They have given here directly the drawing as well. They have given here. Now go and check that where is site. If not, site condition is not given, then you have to raise the query. You have to raise this requirement that you require this data for the calculations purpose, and when you are purchasing equipment, then also this data will be required. Okay, three-phase. Okay, general technical requirement, standard, blah, blah, blah. This system parameters I will take in my next class. Okay, description. This I will take in my next class, system parameters. System parameters I will take in my next class. This all I'm going to discuss in my next class. Approval procedures, okay, that you need to go through that approval procedure as well. And then you need to check the scope of the work we have checked here, AC and DC, that also we will discuss in the next class, the AC and DC voltage, which is they have mentioned here. Here AC and DC voltage they have mentioned, so that we will follow for the auxiliary system design. Okay. I think you all also can download this tender in your system. Otherwise, I will share one project which we recently finished, so that also you can take. So now they are putting the circuit breaker. Anyway, you have to check here the site, then disconnector rating. Please go through and check the site environmental conditions requirement. This is important here. So the point is that following the site conditions are important, which affect the substation designing the pollution level. Based on the pollution level, you will decide your three-phase distance. So which is very much important. This pollution level should be mentioned in the technical specifications. Let me check here if this control F, POWLUTION pollution. Is anything coming here? WUTION pollution. Computer is a little bit slow. Yeah, housing and okay. Any other pollution levels? Yeah, could you see here? They have given the pollution level. Minimum total three-phase distance for heavy pollutions. So they have given the three-phase distance, and they are taking the heavy pollutions. So as I told you, you require the pollutions level of the, yeah, could you see here? They have mentioned here the pollutions level, which is heavy. As per 60815, heavy class 3 pollutions. So you should check here what is the pollutions level. In your case, it is heavy pollutions, polluted area. What is the seismic zone? What is seismic level? Which is required when your civil will design this foundations, they required for the structural calculations foundation. What is seismic zone, where you are making particular substations? What is altitude above ground level? Because when you are going above ground level, your air density going to increase or decrease? Your air density going to
Decrease.
decrease, right? Your air decreasing right now when you are going above ground level. So I do not take ground level, I take the sea level as a reference. So you check what is your altitude above ground level. If you are not able to find all these things, so please copy and go and paste here, and then you check. These all things should be mentioned in the specifications. Altitude above sea level, which is important. I will take this in the next class, and I will see. Could you see here? Altitude above sea level is below 1000 meter from MSL mean. MSL stands for the mean sea level. Below 1000 meter it is here. So it is important. You have to check this. MSL you check. Ambient air temperature, yes, because on the temperature resistance vary. So you have to check what is temperature. Humidity, what is the site? Thunderstorm days per year it is required. What is rainfall conditions? What is the wind speed there? According to the wind speed, you have to design the structural. What is the snow load there? It is also required. So this all things we have to check in my step 4 when I am going through any project specifications, and note down separately on pen and paper that this is my site conditions. So for each calculations, each piece of equipment when you are purchasing, you make sure that equipment manufacturer is making the equipment as per your particular site conditions. So what I'm trying to explain that equipment shall be designed for use in geographical and meteorological conditions as per the project site. That you have to again make sure. So when you are at the site, we have very polluted area, we have very less site space, we have the dust storm. In that case, we do not go with the AI substations. Like here, if you show here, we have AI substations. So, but in that case, when space is less, temperature is very much high, then we don't go with the AIs, we go with the GIS technology of the switchgear. We go with the GIS type substation. So where the site land is expensive but less available, in that case, the GIS type substation is mostly used, and where the pollution level is very high, or where the site temperature is very much high, then GIS type substation is preferred over the AI substations. And in GIS, the equipment protected from atmospheric air, moisture, contamination from the atmospheric conditions, and as a result, GIS required less maintenance compared to the AI substations. So what I will do, I will take in next class, I will take this one. I will go with the ETAP and I will see that when I'm changing the temperature, then what is effect coming on the equipment rating. And when I'm changing the altitude above ground level, so what effect coming in the equipment, so that we can understand more about the site environmental conditions impact on the electrical equipment. Okay. So that I will do, and then again, other steps I will cover in the next class. So let us conclude what we discussed today. What we discussed today. What is our main learning today? Let us summarize what we discussed. Could anyone tell me? Could anyone summarize where we started and what topic we discussed today? I think you all could unmute.
Sir, may I?
Yeah, yes, sir. Yeah, Harshit. Yeah, anyone.
So today we have discussed about the base, type of base.
Type of bay already we have covered in the earlier.
ICT, sir.
Yeah. So we discussed that in the scope of the work, there was word in one scope of the work, there was transformer written, and in second scope of the work, there was ICT written. So we discussed the difference between these two words. Then we discussed the type of the power transformer we discussed, right? Type of the transformer we discussed, not the power transformer. That we discussed. And then we discussed type of the power transformer as well. Type of the power transformer based on their applications. Type of power transformer. Here we discuss overall type of the transformer. And then what we discussed here, that if my HV voltage to LV voltage ratio is less than 2,
less than 2, then we use ICT.
I'll tell you now. I'm adding one more important point, one more additional concept here. What I'm telling, this is correct for the Asian country, but when I go to the UK and other US, in those countries, what they are doing, I told that when HV to LV ratio is less than 2, then go with the ICT. What they are doing, they are making the substations like 132 by 400 kV. A reverse, you can also understand, like 400 kV by 132 kV they are making substations. And in that case, even though my HV to LV voltage ratio is greater than 2, but again they are using the ICT here. Auto transfer they are using here. Means this is like correct for the Asian country, but in this country, for the additional cost saving, they are going with this voltage also at the ICT level. Provided your system should be grid, your voltage should be grid voltage, not any distribution voltage. So 132 kV is grid voltage and 400 kV is also grid voltage. So there is no any source of harmonics here. So they can go with the ICT even though voltage ratio is more than 2 here.
That single phase auto transformer?
So, one more thing. So now we are entering into Q&A session. So any engineer who have cleared the class, they wanted to leave, so they can leave now. So we are entering into the Q&A session. Okay. So 9 to 11 is my time. Now I'm entering into the Q&A part of.
Hello, sir.
Yeah.
Hello, sir. I have one query, sir.
Yeah, 1 second. Before Harshil, let me. Who asked about the ICT? Farhan, did you ask? Who asked about the ICT?
Sir, I
Farhan,
asked about I
Farhan, you asked. Yeah, you tell me what is your query.
I was clear. You give it answer. I have another question about reactor.
Mhm.
Can I ask?
This ICT is clear, right? This
Mr.
ICT.
Raghav, actually, I have a question here regarding the ICT transformer, because you're saying that if HV by LV, if it is less than 2, normally it should be for like a grid voltages. But in my project, the transformer rating is 115 by 34.5 kV, and the vector group is capital Y N A small y N 0.
Mhm.
So I hope this is the auto transformer, right?
Again, you tell me why.
Yeah, capital Y, capital Y, capital N, A, small y, small n, 0. This is the vector group for the transformer.
This is our transformer. Correct.
So,
You can see
so
A
why?
here.
Yeah. Can you please inform let
This
us know why?
34.5, this 34.5 kV, they are using for the like end user, end consumer.
Yeah, for the end consumer. Yeah.
And like, okay, and
Like you can say, this is like a port. Actually, a port they have so many substations. So, and this substation is feeding to the all the remaining substations.
so
You can say.
means 34.5 kV you are taking, that 34.5 kV you are feeding to a next substation, right?
Yeah, correct. Yes.
Okay, and in that substation you might have a like delta transformer as well.
I'm sorry.
In that substation you will have one more transformer, then one extra, na? Because 34.5 kV you are taking from this auto transformer, right? And then again you will step down to 11 kV or something like that.
Yeah, and that means in the same substation, no. Maybe in the downstream, yes. Maybe it is available in the downstream.
Yeah, means there is one main source substations, and then there is a different more substations, right?
You can say a number of substations.
N
Yes.
number of substations means from these substations you are not feeding directly to the any particular load, right? No any
Correct. Yes. Correct.
direct no any direct load connected. You are connecting a chain of the substations again, and in that chain of the substations you will have another transformer, right?
Yes. Correct. Yes.
Means so here I can take the chance because directly no any load coming on this transformer, directly no any harmonics coming on the transformer. So I can go with the auto transformer here as well, which I'm telling here. Srinivas.
Yeah. I'm with you, Mr.
Which I'm telling you means I told that this is first of the great practice which I'm telling you. I'm telling in Asian country we follow this kind of the great practice for the transformer type selection, but I have seen in the country in UK country or US country that in their grid they don't have this HV/LV ratio less than 2. They have 132 kV by 400 kV. They are going with the 400 kV by 132 kV. In that kV case, they are also using the auto transformer ICT they are using. So do not follow this my statement as a what I can say. 100% do not follow this statement, my statement. I'm telling this will change when your country changing, and like in this case also you don't have the load. You are not there's another chain of systems are coming, so you can go with this as auto transformer and voltage ratio again greater than 2, right? So,
Yes. Means since there is no any the effect of changing the harmonics, so That is the
Yeah.
reason maybe they use
Yeah,
it
because you are not connected with the load.
directly with the.
Yeah, so because what we do when we come with the load, which, and if I connect auto transformer, so in the auto transformer, your HV and LV both are electrically connected, right?
Yes, yes, correct. Yes.
So whatever the harness you are putting, that will come in the HV binding, and that will feed to the HV system as well. So
Sure. Yeah.
which should be
Yeah.
allowed, so, which should not be, which we should avoid. So that is reason. If I'm coming on the final distribution, so I will use again the 2-winding transformer.
Got it, Mr. Raghav. Thank you,
Yeah,
thank you
so
very much.
actually, I'm telling the sentence as per the industrial practice. So I'm telling that do not like 100% start fighting with your manager if you deviating by with my sentence. So that could be deviated. But I'm telling you, this is all the things for the cost saving purpose.
Also,
Yes,
one
yes.
thing actually, if there is a transformer in the downstream, actually for the station load, what the auto transformer is okay. So for example, this 34.5
For the station
kV.
load, we will take 2-winding transformer. We will not take this.
No, that transformer should be connected to this 34.5 kV. You know, the primary of the station transformer will be connected to the 34.5 kV. No,
Yes.
as you mentioned.
Yes.
So that is also going to feed to load only. No.
Yes, correct. But
In
what
that
I'm
case,
doing,
auto transformer.
what I'm doing, see what I'm doing. I'm taking a. Let me draw the auto transformer symbol as well. So for the auto transformer, we draw this kind of the symbol in the drawing. What I'm doing in this auto transformer, do not change the class direction. I'm not on the transformer. I'm under scope of the work. But anyway, just to tell you, I have a delta winding here also, okay? Which is called as the MMF winding, balance winding. We have a balance winding, you know?
Okay.
We have balance winding.
No, this was
Let us forget about transformer. We'll discuss model number 3. We have a dedicated model for the transformer.
Okay, fine.
Here I have a delta MMF. I have a tertiary winding transformer. That tertiary winding is delta connected, and that I connect to one transformer, which again will be 2-winding transformer. And then
that I actually worked on. We have the tertiary winding. That tertiary winding will be connected to the station transformer.
Yeah. Okay.
And one more thing, this if the reactor is connected to the line, actually.
See,
So
Rajkumar. So we should understand what I'm discussing. I'm discussing scope of the work right now.
Yeah. Okay. Fine. Okay,
I'm not discussing on the transformer selection. I'm not discussing like that.
Okay.
What happens now, because I wanted to suppose your work by chance I developed 220 by 33 kV substance. So you didn't see the reactor in this particular live project, but by the chance you were working with in company that have 400 by 220 kV substations, and then you will see this kind of the work. So I was covering ICT to explain about this scope of the work. This is what the intention. I have a dedicated module for the transformer. Okay. In that, I'm going to discuss about the transformer selection, each and everything, whatever you doubt. Okay.
Okay. Hello.
Then you will come with your doubt. I'm sure that I have covered your doubt. You don't will have any kind of
okay.
Transformer selection, sizing, protection, case study. These are all here. Okay. Yeah.
Hello, sir.
Yeah.
Hello.
Yeah. Then what we discussed, let us summarize. So first scope of the work we discussed, then type of transformer, then what the third point we discussed today. Then what we discuss about the reactors, right?
Reactor and reactor.
We discussed that when required, what is the criteria, and we took that one 300 kilometer, 350 kilometer line. So required when this is 100 kilometer line, then reactor not required. So when required, we discuss about the flow of power flow, which is a important concept that we, as an electrical engineer, we should know. Power flow direction, active power flow from higher voltage angle to the lower voltage angle, reactive power flow from higher voltage magnitude to the lower voltage magnitude. This all we discuss. And then we discuss that in the ETAP study, the negative sign coming, it means this much power I'm injecting into the grid. Grid is a combination of 1,000 number of generators. 1,000 number of generators is a combination of the grid. And I'm supposed to take the power from the grid, but I'm now feeding power into the grid. So this negative symbol coming, that we discuss. And then we discuss about the reactor connection in the substations. So we discussed that there's two kind of the reactor connection possible. It could be connected with the line in the center, or it could connect with the bus bar in the center. And then we discussed that if the reactor is connecting with the line, so the reactor must have a NGR. This NGR is not neutral grounding resistance. This NGR is still for the neutral grounding reactor. Why this reactor is required? Because this reactor is required for the single pole auto reclosing, to provide the facility of the single pole auto reclosing of the circuit breaker, and to minimize the transient recovery voltage in the circuit breaker. Means when the circuit breaker poles is separating, so in the during the pole separations there would be a like a transient voltage will form. So if the transient voltage is forming between the breaker, so this breaker, even though isolated, but it will not isolated, the arc current, the arc will be present between both moving and the fixed pole. So we need to minimize that arc current, we need to minimize this transient recovery voltage. So this all facility is provided by the NGR. So we took by NGR, I'm telling NGR required, so do not follow my words. I'm telling on the reference of this IEC 60076, part number 6, page number
92.
97. This is the advantage of the class now, so that you remember standardly, remember the page, so that directly you apply when you are working on the project. No?
Sir, I think 99 it was.
What is the page? You will remember, I'm not focused on that.
I thought
This is for you.
Yeah, 99 it is.
97. Yes.
99 the PDF page, but this is standard 90.
Yeah. Okay.
That's okay. So, sir, what I was asking that is the NGR is a separate reactor, or the line reactor is inbuilt?
Separate piece of equipment. Separate reactor.
Just like
this reactor could be, again, it could be oil filled type reactor, or it could be a dry tap reactor.
Okay.
Or oil filled reactor. So when the rating is small, so we go with the dry tap reactors.
Sir. Then another question.
Separate.
Sir, I was asking another question. That is, what will happen when load comes to the?
So what we discussed, the next topic, what we discussed today. What is the next topic we discussed today? Scope of
environment.
Environment. So we discussed that this the area occupied by the substation is large. So as an electrical engineer, you do not only concentrate on the electrical parameters. You have to also cross check what is my site environmental conditions. So when you are going through a technical specifications, please make sure where your site environmental condition is given. If not given, take from the client what is site conditions. Make a list of your site conditions. Ensure when you are purchasing your equipment must have the same site conditions as you have, and this all you have to convey to your procurement as well. The company from where you are purchasing the equipment as well. The same site conditions when you are doing the calculations that you need to incorporate during the calculations as well. Right? The electrical calculations plus the civil calculations as well. Plus what we require from the site, we require what is the soil bearing capacity. This required to your civil team when they are making the foundations of the equipment, soil bearing capacity. Then you also require what is the soil resistance, right? No, resistivity. What is your ground resistivity? This also you require. The soil resistivity value is also required. or this is called as the, what is called this earth? What is report? What is the report that report? ERT report, right?
ERT.
ERT report, the electrical resistivity test report. This again you have to do that, and based on that ERT report, you have to perform your earthing calculations. Earthing calculations. In the earthing calculations, you will take the value of your soil resistivity as an input, right? So site conditions, soil bearing capacity, ERT, this all you will require from the site for the application. So in the next class, I'm going to do ETAP, and I will show you when I'm changing the site conditions. So what is effect on the equipment rating coming, and after that we will discuss the remaining points, how to read a technical specifications when I'm doing a detailed design for the project. Okay.
Sir, can you share?
Sir, hello.
Yes.
Hello.
Sir, I have two doubt on reactor. My first question is the reactor which we are taking in line, its MVR rating is fixed or it is kind of variable rating it has?
See, the rating which I am taking, it is from the specifications, which is 125 MVR.
Sir, if a specification is not given for IPP,
that the system planning or transmission planning team, they have to do a feasibility study before coming to the tender of the project, and they will decide based on the line length what would be the reactor required. Now this reactor is the fixed value which would connect or not connect with your substations, and nowadays we are moving from the fixed reactor to the variable reactor, and due to that reason we have the SVC StateCom which is coming into the substations. This is a new technology. The StateComs, static war compensator, SVC. In that, no need to take a fixed value. We will regulate the reactor value based on the system requirement. Okay, sir.
Okay, sir. Clear.
Yeah.
Sir, my second.
As of now, in this particular, this is fixed 125 MVAR.
So at a time, 125 will be connected or not connected?
Not connected. Yes.
Okay, sir. My second question is, as we have reactor switchable, so that switching is done manually or we have some auto kind of.
Not manually. It is done remotely, automatically, using the circuit breaker based on what is the power flowing in the system during operations, and this is done by your what I can see, the load dispatch, the LDC, or what we LDC. You aware about the load dispatch?
Yes, sir. Sir, suppose operator or engineer who is sitting at SCADA room, he watches or he need to regulate.
The operator, I don't think this all is operator responsibility. This responsibility is the who are maintaining or regulating the entire grid are the load dispatch centers. They will do this kind of the things.
So, sir, they do it by manually or there is
No, they will do
ABR?
remotely. They have they will connect with your substations. They are connected.
Sir, I am getting that, but do we have in this AVR kind of system to regulate?
No
And there is a power factor controller which actually senses the requirement of power factor for MVR and which switches on the capacitor bank as per requirement for reactors as per requirement.
So this is done auto or
Yes,
means
there is a controller. Yes, there is a controller that will detect and that will switch on the reactor.
I think Mr. Pandey is
Raghav sir, can I say
Mr.
something to
Pandey is asking That is the automatic regulation, or I mean that,
Raghav sir.
that part, right?
Hello.
Yes, it is automatic regulation.
Raghav sir.
Okay, thank you.
Hello.
Yeah. I
Can I say something to Saurav if you don't mind?
Yes.
Hello. Saurav, actually I was working at 400 kV grid substation Padga. So it was our duty to inform a load dispatch center that our bus voltage is increasing. And then they used to issue us a code. Like then they used to speak with the National Grid Center, and then they used to take a code, and then they used to give us a permission to get your bus reactor into services. And we used to do it remotely. That's the procedure which follow at the grid substation.
Normally, that is the procedure. The load dispatch center only will inform the substation to switch on or switch on the reactor.
Yeah, it's a duty of load dispatch center.
Yeah. They only are monitoring the power flow. So they will advise the substation operator to reduce the reactor or switch off the DNS reactor.
So in this,
What about for the smaller substations?
In this, load dispatch center would tell us whether means they'll give us code, and then we need to take action on it, whether to switch on or switch.
Basically, it is also our duty to inform the load dispatch center that your bus voltage is increasing, because at our substation it was 420, then above 425 there was a guideline given. If it is after 420, 425, you need to inform load dispatch center also.
But in this process, there will be some time will be consumed, na?
No, it's just immediate. They will just issue a code, and it won't take any time.
Okay.
And what about smaller substations like voltage level of 220 kV, 132 kV? Will they follow the same thing or?
Hello. Anyway, your load dispatch center is also monitoring your substation as well.
Actually, sir, my question was as in OLTC, we have AVR kind of system which will automatically sense and changes the taps of OLTC. So this kind of system is with reactor also, that I wanted to know.
So my knowledge, it is no. There is no controller. We have to close the reactor by panel. That means through a circuit breaker, we have to close the circuit breaker. That reactor will be energized. There is a controlling switching device is there. That is for the closing pulse. But which pulse location we have to, the command will should execute like that. That is there is a device for like AVR. There is no device for the reactor.
So we don't have the AVR. We don't have the OLTC.
Okay, thank you, sir. Thank you, Nikhil ji. Thank you. Ram.
Hello, sir.
I hope now clear. Saurabh, are you clear?
Yes, sir. Yes, sir. Now it is clear. Thank you.
Hello,
Thank you, sir.
Hello, sir.
Yeah.
Sir, kindly open the ETAP, sir. Yeah. Sir, in this condition, sir, yes, sir, 0.0, sir, before your training session, this time, there, sir, some megawatts are indicated. This power will be as a power charging current, sir. Transmission line charging current, sir.
No.
Indicated.
No. That current is not the charging current.
Okay, this is the reactive current, sir. Reactive power, sir. They induce in the system by the capacitance, sir.
Yes.
But active power is not a so. Sir, remove the sir. Yes, sir. Remove the load, sir.
Service out.
Okay, sir. Yes, sir. What is the meaning of the 1.4 megawatt indicated,
1.4 megawatt, because this here
for a line charging?
Yeah, you can say the line charging, yes.
Okay, no issue, sir. Okay, thank you, sir. Hi.
Sir, what will happen if we connected 100 megawatt load in this bus? In this case, shunt reactor, how to reply?
100 MVR load, 100
megawatt load to the receiving end.
Separately, right?
No, separately. It's from connected from grid. That my sending substation sending 100 megawatt to the receiving substation, and then what will be the megawatt condition actually? And in this case, what will?
Yeah, in this case, no, what?
What will do with our reactor? Will it be opened or energized with the bus?
See, under if you are getting 400 kV regulated voltage, if you are getting this voltage, no reactor required. No any reactor required. If I'm able to maintain my bus voltage, I'm putting the reactor because my bus voltage jumping to 430 kV. Due to that reason, I put the reactor over here.
Is it the same concept of the capacitor bank we use in our system? That we
Similarly, similar kind of the concept when we have the like power factor, which is like poor power factor, and then I can connect the capacitor bank and we can improve the power factor of the bus at point of
yes,
similar kind of the.
Okay. Thanks.
Yeah.
Thanks.
Hello, sir. Sir, what will be the case? We are using NGR, right? And if it is connected to transmission line, shunt reactor is connected to transmission line. So if there is a 3-pole auto repose, because in UK, sir, if you will be using 3-pole out there only, delayed auto repose function. So in that case also, do we need NGR or only for single pole auto repose?
See, we require auto reclosing only for single pole auto reclosing. If I have a 3-pole auto reclosing, like in case of the bus bar, when we have the reactor with the bus bar, so we don't. Could you see here in the bus?
Yes,
in the bus, there is no any temporary fault, right?
Right.
So in this case, would my reactor require auto reclosing, single pole auto reclosing? No.
No, not needed.
Not required here. Auto reclosing would be always TPAR, 3-pole auto reclosing, right?
Right.
So here NGR not required.
Okay.
When I have a unbalanced conditions during, and could you see here the IC during unbalanced conditions? When I have unbalanced condition in single pole auto reclosing, my RY phase is closed, B phase is tripped, right?
Right. Yeah.
So when I have the unbalanced system, and whenever I require single pole auto reclosing, then only I require the NGR.
Okay, sir. Okay. Thank you.
Thanks, Arvind. Thanks.
Sir, I have a doubt, sir. So during ETAP, just you mentioned zero sequence, positive sequence, negative sequence, and you mentioned that for zero, it's a triple time of the positive sequence. So can you tell the why it is triple the time of the?
I'll come on that later on, because this zero sequence we represent like 3 I naught, like that we represent. Okay.
Okay.
So due to that reason, it is generally multiplied with 3 times with your positive or negative sequence. But even though this zero sequence represented at 3 I naught, this is the symbol to represent zero sequence. Okay. This is all part of discussions that we will discuss later on. But in just to quick reply your questions, zero sequence means 3 I naught, correct?
Okay. Yes.
So that is it is 3 times higher considered compared to the positive sequence. If you see here, 0.7 multiplied by 3.
Okay, I forgot. Okay.
Okay, thanks.
Yeah, and one more doubt. So last section we are talking about the cables. So for that time also we are talking about the reactors, right? So the same concept it will be repeated, right?
Yes, same concept.
What we taught you today is the same concept for the cables shunt reactor.
Correct.
Okay.
Yes. Same concept.
Okay, thank you.
Thanks, Krishna. Okay, so should we wind up today's session? And
Hello.
yeah, Suraj.
What is difference between web trap and reactor?
I will discuss this in the module number 2. Okay, Suraj Yadav.
Okay, sir.
Yes, wave trap is a different equipment. Wave trap is designed to filter the high frequency signal and low frequency signal. So wave trap stop the high frequency signal and they allow to pass low frequency signal, because if you check the formula for the in reactor, so what is your XL? It is 2 into pi into F into L. So when your frequency is high, so your XL would be high. So this reactor is a kind of the equipment which and which like passes or which have higher impedance. Actually I'm putting higher impedance when there is a high frequency signal, and this will have the low impedance when there is a lower frequency signal. So it means this wave trap allowed to enter a 50 Hz signal, and wave trap will stop the high frequency signal. So what we are doing that from one substation to the next substations, we do the communications, and this communications we do in form of the high frequency signal. This signal comes in the terms of the kilohertz. It could be like 100 kilohertz or 200 kilohertz. In this range it could be, which is established by the telecommunications department of the substations. So between this by this high frequency signals, two substations are connected with each other with for the telecommunications. So what I'm doing here in one substations, high frequency signal coming to the next substation. So what I'm doing that I'm putting a wave trap equipment here, and after that I'm putting to the bus bar, and this wave trap equipment will allow to pass 50 Hz signal, because 50 Hz, so F is less, so overall impedance will less. And when any high frequency signal is coming, which comes into the kilohertz, so your F is high, your XL would be too much high. So it will stop the high frequency signal, communication signal, and it will be diverted to your communications equipment in the substations. Okay, Suraj Yadav. Anyway, I'm going to take this all things in the detail in
Yes, sir. Okay.
model number 2. I try to explain it in a briefly, but anyway, this is part of the model 2 discussions. So you don't bother about if you are not getting these things.
Hello.
Yeah. Okay. Thanks. If you understood, then it's fine for me.
Raghav, why we are using this multi-winding transformers for the
multi-winding transformer we are using because we have, when we have more than one power source, then we use multi-winding transformer. I took the example of the solar power plant.
Yes.
So could you see, I'm not able to show you the inverter here, but could you see, this is IDT over here, okay? Inverter duty transformer in this solar power plant. So as I told, when you are in a company make the solar power plant, so they create this solar power plant into blocks. Okay, Manoj. Okay. So like if you see here, could you see here in this there is a lot of 1, 2, 3, 4, 5, 6, 7. Could you see here?
Yes.
So this is my one block. Generally 6.5 megawatt. We go with one block like that. And here I have the inverter. It's a central inverter, and here I have the inverter to the transformer, and this is my, what I can say, auxiliary system for the lighting of this entire area. Okay, so what I'm doing here, I have the what I can say means the table here, PV model table. Okay, PV models tables, and after that we have the inverters. I don't think you see the inverter here. Inverters, and from that inverters, from this table we have the inverters, and that I'm feeding to this here, one central inverter here. So here what I'm doing that I'm putting here a multi-winding or 3-winding transformer. it could be 5-winding transformer. It will be more clear when I will take a solar power plant SLD, then it will be more clear, which I will take in the SLD module. So in that, I'm taking the power from different PV tables, okay? PV tables.
Okay. Okay.
And then from power from different PV tables, then feeding to one power transformer here, which is like a multi-winding transformer here. So some power coming from this inverter could be 3.25 megawatt, 3.25 megawatt coming from this, and then coming to here, and altogether 6.5 megawatt on the HV side, and that we are feeding finally to the A power transformer, and which is stepped up and will feed to the grid. Anyway, I'm going to take this out in the solar SLD. When I will discuss that, I will show you in the SLD. It will be more clear then. Okay.
Okay. Okay.
So
Thank you.
to be brief, if I tell you when I use multi-winding transformer, so when we have more than one power source, more than one source, then I will go with the multi-winding or 2-winding, 3-winding, 4-winding, 5-winding kind of transformers.
Sir, can I ask one question? For example, you are asking different sources, like it means the number of the inverters feeding on the LV side of that transformer, right?
Yes. I'll take this in the solar SLT when I will discuss. So
yeah, I want to share my solar farm, like where I am currently working as site engineer. We have 32 inverters. Okay, basically feeding one station transformer. We call it STS. Okay, so they are taking the like 800 volts line, 0.8 kV, and then stepping up it to 33 kV. So we have like 2 star and 1 delta. Like
yeah, so again 3-winding transformer, right now?
Yeah,
2 star 1 delta, so 3-winding.
Yeah, 3-1.
Yeah, the similar thing I was trying to explain to Manoj as well.
Yeah. Okay, thanks.
Yeah, thanks, Amar. Thanks for sharing your project example as well.
Hi, Raghav.
Yes.
Can you please, because my internet was having some problems, so I just lost the some portion of the class. Can you just tell
Okay,
a little bit, just we will go back about NGR. NGR and single pole auto reclosing, and also that to protect the transient. Yeah, even the SLD also, yes.
Yes, I'm here.
Yeah, say this one auto single pole auto reclosing, correct? Single pole auto recloser, yeah. Can you just little bit brief?
See, brother, I will take this point in my breaker class. I think you did not follow due to your internet down, because I have told that this is part of my breaker discussion. So when I will come on the breaker, I will take up the single pole auto reclosing in the detail. I will take up in the breaker module along with that.
Okay, fine. Okay. And also one more thing, this NGR we are using in line transmission lines along with the reactors, correct?
Correct.
And the purpose for the NGR, the purpose for the NGR is to minimize transient recovery voltage, and also there was another. What is that you said before?
Yeah. So here we have.
The one point I got that
the secondary arc current. Secondary arc current.
Secondary arc current. Yeah. Okay. Thank you. Got it.
Okay. So, were there any query regarding the scope of the work which we are discussing as of now?
This is fine. No problem. That's okay.
Switching substations have which type of power transform? ICT kind power transform circuit. Switching substation have ICT.
ICT, right? Okay. So the transformer used is on the, like there is no kind of load there, right? In switching substation.
No load there. Only you are connecting, just taking transmission line and then bus bar, and means to be honest, Sakib, we have to see what is the configuration of that switching substations. Whether I'm just taking 400 kV, step down to 20 kV, I'm transmitting to 20 kV. What is the goal of that particular substations? So that also we have to.
So there may be load and there may not be load.
Yes. So if there is no any load, anyway, we will go, if I'm taking 400 kV and switching to 220 kV and then 220 kV transmitting, so that would be obviously the ICT we will use there.
Okay, thank you.
Yes, okay. Okay, thanks all for your valuable time. So tomorrow 9 p.m. again we will meet for the remaining point, how to read a tender. 8 technical specifications. Okay. Thanks, Rajkumar. Thanks all. Thank you, Hari, for sharing your feedback with all of us. And again, congratulations for you. Okay. Thank you. Thank you, Sarah.
Thank you, sir. Thank you all.
Thank you. So like Hari said, chance their random carry into the designing. So others, please also be sincere. Like who are as of now working in random testing.
What's that, Raghav? Hari?
Like there is one participant.
Can you just tell me what is that regarding Hari?
He was working as a O&M engineer and now he's selected as a design engineer in a company. So he faced interview last week. So he was telling this week. So he was telling what is their feedback during the interview, how this course helped him. Okay.
Okay, fine. Thank you.
So if it's okay with Hari, can Hari discuss the question what they asked for during the interview on the next section or in WhatsApp or something?
See, all their interview questions we are covering in the class. So if you
Yeah, obviously you will be
if
covering
you follow
areas.
you will use, to be honest, if you follow the class, any questions will not come out of the discussions. Anyway, the questions was about the bus bar schemes, about the earthing calculations, about the standards for the equipment. These things they have asked during the interview questions. Okay. Thank you. Thank you.
Thank you.
Thanks all. Thanks. Thank you. Good night. Meet tomorrow. So, okay.